Good afternoon, everyone. My name is Natasha from Vermaak, and I want to start actually by saying that recently, for the last 2 years, I was a postdoc in University of Grenoble, and when I arrived, I saw the thesis defense of Lauren Lessig, the previous speaker, and I was inspired. I was inspired by this shape and topology optimization method. I thought, let's continue along this direction. Let's use multiple materials. And since this method is so robust for tracking interfaces in particular, let's take interfaces seriously. So I'm going to be presenting today, this afternoon, with my colleague, Georgios Michailidis, some work that we did in collaboration, and with the advisement of Professor Perry, Estevez, Professor Jouve, Allaire, and Bréchet on shape optimization for interface design. So I have a subtitle, Using the Level Set Method for the Design of Multiphase Elastic and Thermoelastic Materials and Interfaces. So I'm going to be giving some background and motivation for using this level set method in a new way that takes into account material interface effects. I'll also be presenting some benchmark problems in materials design that we've applied it to, and my colleague is going to continue from there. So we're focusing also on a method here and showing some applications of the method. We're taking as inspiration the architectured materials that many people have been working on for quite a while. I just happened to take the definition from Ashby recently in a paper from 2013, combinations of two or more materials or materials in space configured in such a way to have attributes not offered by any one material alone. So I've emphasized configured here because what we're doing is we're saying that we can benefit from many different tools that help guide us in best configuring materials in space. So the addition here that I've made is best configuring, and that immediately lends us to ideas of optimization. So the tool we're choosing to help us guide configuration of materials in space is topology optimization. And I happen to like, as an American, this simplistic view in 2D of topology optimization that equates your morning coffee cup with your American donut. So the French croissant won't work here. But these two, in 2D at least, can be considered topologically equivalent. And the type of topology optimization, again, is the same that Lauren presented previously. Now, instead of black and white for materials or matter in space, we introduce two materials at least to start. And our level set function in this very simple schematic is a cone. This function always has to be one dimension higher than the problem of interest. Today we're sticking with just 2 dimensions. So our 3D cone intersects the 0 level set, and that intersection then defines the interface between my 2 materials in blue and yellow. So this is a very robust way for tracking evolving interfaces. And as a materials scientist or a person interested in mechanics of materials, immediately I'm interested. But this method has wide use across a number of different fields, including things like image processing. So as this method allows us to track interfaces, we have a choice about how we decide to model those interfaces. For example, if we just look at metals, we can understand by interface many different things. For something like in semiconductors, we can have sharp interfaces. At the atomic scale, we can look at the simplistic view at an either-or, a very mathematically sharp boundary. But in reality, or in many cases, we have graded or smooth boundaries. And we can control those. We can control them through interdiffusion. We can control them by surface reactions. We can control them now specifically with additive manufacturing. It's an exciting time to look at interfaces. When we apply this concept to the level set method, then we introduce our interface model. So between 2 materials, Between two materials, we're now going to introduce a finite zone over which we grade or smoothly transition the interface properties. So for now, in my 2D problems, I'm going to make sure, I'm going to fix this interface zone to be uniform throughout the domain. And across that domain, then I can choose how I wish to portray the transition from one property to the other. So we have bulk materials with bulk properties, for example, Young's modulus, and over my finite interface zone, I go from high to low in a sort of smoothly monotonic fashion. But we could also use non-monotonic functions, because in many systems, material systems, we've heard of some today, including steels, the interface properties are not simple averages of bulk properties. We can have interface properties that are the strongest link or perhaps the weakest link in your system. Today I'm going to focus on a case that's good for the interface, when the interface is the strongest component in your system. And we show for structures first. I'm going to just highlight some of the things we learned when we applied this new approach or new perspective with structures, and that will hopefully motivate us for our materials design. Here's a very simple example of minimizing compliance of a built-in beam under a vertical load at the midsection. And we're going to use two materials, a blue material which has a high modulus and a yellow material which has a low modulus. The ratio between these two moduli is 10:1. And when we try to then initialize a half domain with a matrix of the high moduli material and inclusions of the low modulus material in yellow, in red I've just highlighted the interface for now. We initialize, and using the same method that Laurent presented previously, we then come eventually to some converged design, which I show on the full domain here on the left. This final design, which gives us a non-dimensional compliance of, the number is not important in this case, but 3.25. This is a reference case. This is a typical problem in the literature for compliance minimization, minimization of compliance. All right, now what happens, where we're really interested in, is when we change the model for the interface property transition. If we now look at non-monotonic cases, so on the left case, we're just going to really artificially improve the properties of the interface for now and ask what happens, and then really make the interface beneficial on the right-hand side. So in this case, we have some properties over the interface zone, and our interface property happens to have twice as large as any of the bulk, and on the right-hand side, 5 times. Let's really push this to see trends. And what we see is that, again, there's a volume constraint. This optimization is done under the volume constraint that you have to use at 50% of this domain has to be the weaker modulus material. And we see that the optimization finds ways to increase the perimeter of the interface, of this beneficial interface, while still respecting the volume constraints on the problem. So again, we've pushed this trend just to see what happens, and you see the influence of the interface. It has allowed us to go from compliance of 3, non-dimensional compliance of 3 in the normal standard case to a 1. So there's significant benefits here in just this very simple example. We are enthusiastic about this example and many more in the area of structures, and that's inspired us to go on to materials design. So we again start with benchmark literature problems in materials design. And for example, we took the space of coefficient of thermal expansion versus Young's modulus. So useful in aerospace problems, you would want to have low CTE materials and stiff materials at the same time. So excluding ceramics for now because of my bias and my colleague's bias, we have a population of materials in this space. And our goal then is where you see this insert of low CTE lattices. There are many different people who have worked on this over time, including Lakes, Sigmund and Torquato, the Air Force Research Lab, and recently also UC Santa Barbara, where I came from. And again, they're using many different methods. They have slightly different goals, but all of them are related to low CTE. Some of them are looking at combined low CTE and biaxial stiffness. Some of them don't mind whether the structures are bending dominated or stretch dominated. But we're going to focus on examples in low CTE, high stiffness space that were previously investigated also by the level set method by Wang. However, their formulation has recently been corrected by Allaire et al. And because of that correction, we won't be able to show exact comparisons with the literature, but we will show you our first results. And there's 2 examples that we're focusing on. So again, that's we're targeting low CTE properties and shear properties with given volume inequality constraints now with 2 materials and space. And the last thing I want to point out is we're going to show you results first for standard monotonic transitions between material properties, bulk properties, and then move on to non-monotonic, because our overall goal is to really start to take advantage and use material science input in these new shape and topology optimization tools. So, my colleague.
So thank you, Natasha, and thank you for coming to our presentation. Let me introduce myself. I'm Georgios Michailidis. I'm a third-year PhD student at the École Polytechnique of Paris under the supervision of Professors Grégoire Allaire and François Joux. So I will start from scratch, and I will try to explain you what shape and topology optimization deals with let's say, an intuitive way in the beginning. Imagine that you have a design domain depicted here in gray, which has some fixed boundary conditions and some fixed loads. And you are asked to design in this domain a structure that meets some certain requirements. So the question to which you have to give an answer is where to put the holes on the structure. And shape and topology optimization gives answers to this question using tools of mathematical programming. So more specifically, for a problem of shape optimization, you mainly need 3 parts. You need a model that is a partial differential equation which gives a mathematical description of the mechanical problem at play. You need an objective function to be minimized, and you need a set of admissible shapes which constrains the set of shapes in which we search for an optimal solution. So finally, a shape optimization problem reads, find the shape omega that belongs in an admissible set, which minimizes an objective function which depends on the shape and on the solution of the partial differential equation, which itself depends on the shape because it's posed in the shape. So how do we do it? The minimization of such a function does not differ a lot from the minimization of a simple scalar function that depends on one scalar variable. So unless the problem is trivial and an analytical solution can be found, it amounts to an iterative process. So we start from an initial guess point, we call the x0 here. We usually construct a linear approximation of the function close to the point, in a neighborhood of this point, and we take another point x1 that lies closer to the minimizer. In order to construct this linear approximation, we need to calculate a notion of derivative, of gradient. So for us, it would be a shape gradient, which can be understood as a velocity field defined on the boundary of the shape, which tells us how the boundary should change in order to decrease the objective function. So now let's summarize. Our numerical algorithm will read that initialize with the initial shape omega 0, and until convergence, evaluate an advection velocity, and transport the shape in order to get a new shape. So how is the shape described? In our method, we use a level set method, both because it gives an accurate enough description of the position of the boundary, and also because topological changes happen in a very natural way. So imagine here that you need to describe the evolution of this shape in gray, which evolves in time and changes topology. If you had parameterized the boundary of the shape, you would need to change this parameterization at every time detect the exact time where the shape is going to split in two, and construct a new parameterization and so on, which is very difficult to be done. So instead, what is easier to be done is to use a one-dimensional higher function, a level set function, depicted here in red, and reveal the boundary of the shape as the intersection of this function with the x-split plane, the zero plane. So the same evolution can be described by performing much easier operations on the level set function and considering always that the boundary is revealed as the zero level set of this level set function. So more specifically, in 2 dimensions, we will assume that all our shapes will be subsets of a given working domain, of a fixed domain, a rectangle here, and we will take the shape to be the set of points where psi equals 0, the level set function being psi, and by choice we attribute negative values inside and positive in the outside. So we will have a shape that evolves in time under a velocity field u. By doing a derivation in time, we get the following transport equation which describes the evolution of the shape. So with a one level set function, we can describe 2 different phases. So what if we need more phases? Then we can use more level set functions, for example, 2 level set functions, and take combination of their signs in order to describe 4 different phases. So in general, using m level set functions, we can describe up to 2 to the m different phases. So now we have a shape and topology optimization method. That's the combination of the shape derivative and the level set method. And we want to use it in order to optimize some homogenized coefficients using periodic homogenization. So we assume to have a periodic domain of period epsilon that tends to 0. And we want to optimally distribute 2 or more phases in the unit cell, whose position is described by means of level set functions. So using the theory of periodic homogenization, we get a formula for example, for the homogenized elasticity tensor, which depends on the position of the phases in the unit cell through the values of the elasticity tensor in the unit cell and through the solution of some partial differential equations called the cell problems. So let's give an example in order to get a better picture of what we're doing. In this example, we want to optimally distribute 2 phases and void in order to get some target CTE and shear stiffness properties. So the first, material 1 has half the Young modulus, they are isotropic materials. Material 1 has half the Young modulus of material 0, and its thermal strain coefficients are 10 times higher. And we want to mix them in order to find the unit cell configuration, which will give some homogenized coefficients with these values, with these target values here. That the homogenized coefficient will approach as much as possible to these values here. So we care about the shear stiffness of the elasticity tensor and about the coefficients of the thermal strength tensor. One way to do it, a simple way to do it, is to construct an objective function that is a weighted sum of least square deviations between the homogenized properties and the target properties. So then we set some resource constraints in terms of volumes of the phases that we are going to use. We set our weight coefficients for the objective function and some numerical parameters. And starting from an initial random, let's say, unit cell configuration, we get the following optimized configuration. So here we plot the Young modulus of the materials. And here we plot 16 times the unit cell in order to get a better idea of how the periodic domain looks like. And we see that the homogenized coefficients start approaching the target coefficients. So in the second example, we will use again 2 materials. Material 1 that has again half of the Young modulus of material 0, and the thermal strain coefficients 5 times higher than the ones of material 0. And we would like to approach some target coefficients for the elasticity tensor and the thermal stress tensor. Again, we use the same form of objective function we set some resource constraints and an inequality constraint for the shear stiffness. We set a minimum limit for its value. And we, starting again from a random initialization, we get the following optimized form with the following homogenized coefficients, which are close to the target coefficients, while the inequality constraint for the shear stiffness is satisfied. So until now, we have presented, as Natasha said, some benchmark examples in the sense that the interface is monotonic, and either it stands as a monotonic interface or it approaches, numerically simulates a sharp interface. So now we would like to see what is the effect of considering non-monotone interpolation schemes for the material properties. So we take the last example that we have presented, and this time we consider that for the thermal strain coefficient there is a bump in the intermediate interface of the two materials. So this is the profile of the Young modulus, and this is the profile of the thermal strain coefficients. The problem is the same as previously, and starting from a guess shape, we converge to an optimized shape that has a much different form than the previous. Again, we can see that the homogenized coefficients are close to the thermal coefficients, so we are satisfied. And one more example in which both in the Young modulus and the thermal strain coefficient, there is a hole, let's say, in the intermediate interface. So these are the profiles here. And starting from initialization, we get the following shape, and this is how the periodic domain looks. Again, the coefficients are close to the target coefficients. And so we think it's a bit early to talk about comparisons between monotonic and non-monotonic, but some questions that we could pose is for example, that can we see an obvious change in the optimized shape, but can we hope to take advantage of the interface properties in order to create lighter materials with the same target properties? Or can we take advantage again of the interface properties in order to take materials with properties which cannot be achieved with standard sharp interface models? So these are two questions to which we hope to answer soon. Thank you very much.